In this video, we're going to be deriving the small signal diode model, which is of course very useful if you want to be able to quickly analyze a circuit response to a small signal change. So before we start to dive into the actual maths of the model, the diode equation and so on, we first need to define what we mean by small signal. So you can see on the graph on the screen here, we have a sine wave showing how our current changes with time. And we have various different components to this signal. So the IDQ value, the black line here, that's the DC large signal component. And so we notate that with a large I and a large D. And this is standard notation. Then we have the small signal, in this case AC signal, which is on top of the large signal component. So you can see that this wave is oscillating around that large signal offset point. So we notate the small signal as small I, small d. Now at any one particular point in time, we have the actual instantaneous current. That's shown by this arrow here, and could also be, for this point in time, it would be up to here on this part of the curve. So the instantaneous actual current at that point in time is notated by a small I and a large d. So with a combination of both the large signal and the small signal currents. And so that's also expressed in the equation here on the right hand side. So we have our instantaneous current, small I, large d, equal to our large signal current and our time changing small signal. And in this case, our small signal is defined by this equation here. And the ID term here is simply the amplitude of our signal. So to understand our small signal diode model, we use the circuit in the top left of the slide here. So you can see that our voltage is represented as a large voltage signal, VDD, and a change in VDD. So that's our alternating small signal, our delta VDD here. And of course that gives rise to a large signal ID current and some change in current, again the small signal, and then an associated large signal VD across our diode and a change in the VD with the delta VD signal there. And over on the right hand side here we have a typical diode IV characteristic. So here we have the diode current on the y-axis and the voltage on the x-axis. So this graph really gets at what we're trying to do with the small signal model. You can see that our IV characteristic of the diode is very nonlinear, and that leads to some very complex maths and makes it quite difficult to quickly do any kind of circuit analysis. But if we're operating around a small part of that curve, such as the bias point shown here, then as long as we're in this small voltage region, so this is our delta VD limits, we see that the associated change in current can be approximated by this blue straight line. So therefore, if we're operating only in this region, we can assume linearity, and that makes everything a lot easier to work out. So the idea here is that our large VDD supply signal just biases us to a certain point on this diode IV characteristic, and the delta VDD, our small signal, will alternate our voltage, but within quite a small range of the bias voltage. And therefore, if we can work out the slope of this curve, then we can work out the associated current for those small changes in VD. So we have our equations here. We have the diode voltage at any point in time, the instantaneous voltage, being equal to the large signal voltage plus the small signal voltage. So in this case, this small v, small d would be equivalent to the delta VD up here. And similarly, we have the current, instantaneous current ID with time is equal to the large signal ID plus the small signal current also changing with time. Now we know the Shockley diode model equation. So that can be written as ID, the current for the diode, is equal to IS exponential VD divided by NVT. And these parameters are explained in the previous videos. Though it is worth noting that this simplified expression is for the case when we already have at least some forward voltage, as that makes the exponential part of the model a little bit simpler by removing the additional term. So if this is for our instantaneous voltage of VD, that is the small v large d, then we can show that that's also, based on the equation up here, equal to IS exponential the large VD plus the small signal VD over NVT. And just using our simple mathematical laws for exponentials, we know that this equation can be translated into this one here with the exponential terms separated. Now the key thing here is to recognize that this half of the equation is simply the large value current ID. So that's our large signal ID value for the diode. So therefore, if we plug that in, we can simplify our instantaneous current ID is going to be equal to the large signal ID times exponential of the small signal voltage over NVT. Now, if this part of the exponential term here is much less than 1, so if it's very small, and of course what we're implying here is that the voltages, the VD, the small signal voltage, is very small, then we can use the Taylor series approximation, which would state that e to the x is approximately equal to 1 plus x. So you can look into this approximation if you're not familiar with it. There are other terms, but they get increasingly smaller. So this is a sufficient approximation to give us some reasonable accuracy in our result and to simplify the mathematics going forward. So using that for the above expression here, then we get that our instantaneous ID is approximately equal to the large signal ID times 1 plus VD over NVT. And of course, we can then just multiply out the brackets to get this term here. And we also know from our equations up the top here that our instantaneous current is equal to large I large d plus small I small d. So knowing that these two equations are equal gives us the fact that small I small d is going to be equal to this expression here. And what we have here is a current value equal to some variables times a voltage. So this part of the equation here must be a conductance value, being that a voltage times a conductance will give you your current, and that would be the inverse of a resistance. So what we can actually say is that if we do the inverse of this part of the equation, we'll get what's called the incremental resistance, RD, as being equal to NVT over ID. So we can define our RD using that, and that will simplify our current equation for the small signal current down to small signal voltage divided by this RD value, which we've defined here. And as you'll see in the graph on the right hand side, the slope of that curve is of course defined by that resistance and conductance value. So the slope here is 1 over RD. So now we've worked out the equation so that we can find this small signal current change response to a small signal voltage change input.